Okay, now we obtain the governing differential equations for axial and bending and shear deformations. Now what we are going to do is to obtain the stiffness matrix coefficients. So we will first repeat what we did last year, and then we will add the shear deformation to our stiffness coefficients. But let's remember again, we said that we have frame members, and according to our definition, the frame member is composed of or can undergo axial deformation, and it can undergo bending deformation. So we are assuming that these two deformations are independent from each other. So for as a starting point, we will just assume the Bernoulli-Euler beam theory for the bending deformation. Let's remember that we don't have any shear deformation. And if you remember our stiffness method, what we need, if I have a member like that, what we need is a relationship between the end forces, right? You can have the following end forces and end displacements. Now let's take a look at the axial deformation first. And the governing equation for the axial deformation is as follows. It's a very straightforward relationship. Of course, we obtain this relationship assuming that the axial force on the member is constant and the area also doesn't change. Constant area through the length of the member. If that's the case, we have the following equation, and I can directly use this equation to obtain the relationship between the end axial forces and the elongations. To obtain relationship between end forces and displacements. Okay, now let's take a look at the bending deformation now. Now in the bending deformation, we have the following differential equation: d square y dx square is equal to m over ei. So if I want to use this equation to determine the relationship between the end forces and the end displacements of a member, right? It takes too much effort. To solve this equation for each member. Let's continue from the right. Let's say that I solve it, right? What did I get at the end? I obtained the full displacement field. Gives full displacement field. What does displacement field means? It is the equation for the transverse displacement. So it gives me the transverse the full equation. I mean, by using that equation, I can determine the displacement at any point. So this is too much information for us. Why? because in our stiffness method we only need a relationship between the end displacements and end forces. Okay, so in order to do that, what we did is we take a member and we say that, okay, this is the end moment, MAB, this is the other end moment, MBA. So this is point A, or node A, node B. And by using this equation and an assumed deformation field, so we say that that's the undeformed shape. So point A can move in the upward direction, B can move in the upward direction. This is delta A, delta B. And one of the parameters that we use to define the end translation is the chord rotation. We call it the phi angle. And then we can have a rotation at A, we can have rotation at B, and that's the deformed shape. This rotation is theta A, and that rotation is theta B. So with this end forces MAB and MBA, if I have a deformed shape like this, I can use this equation and determine a relationship between the end moments and displacements. These equations are called the slope deflection equations, and we have MAB is equal to 2EI over L 2 theta A plus theta B minus 3 phi, and MBA is 2EI over L theta A plus 2 theta B minus 3 times the chord rotation. So instead of using this or trying to solve this equation over and over for every member, we have the simplified version of that equation that relates only the end forces with the end displacement. So we obtain an equation in the following form. We call these equations as our slope deflection equations. And we use these equations to determine the stiffness coefficients of a Bernoulli-Euler beam member. Okay, let's continue to derive the element stiffness matrices. Now we did it for a beam member. So let's do it for a truss member. So let's draw a truss member now. So here this is the start node, let's call it I, and node J. So just to represent, I is the start node, J is the end node, let's put an arrow sign. And let's show the degrees of freedoms. That's D1, that's D2. Since by definition the truss member undergoes only axial deformation, I just show 2 degrees of freedoms. So case 1, D1 is equal to 1, D2 is equal to 0. So I will be applying the same logic. So for every element that we want to derive the stiffness coefficient, we can apply the same logic. So this is the start node, member, end node. I apply K11 to create a unit shortening, and I apply, take K21 to keep the translation at the end node equal to 0. So the deformed shape will look like this. I have a unit shortening here, and in order to create that shortening, the force that I should be applying should be a compressive force, and its magnitude is EA divided by L. Now, in order to have equilibrium, I should have the same force but in the opposite direction, and whose magnitude is also equal to EA over L. So in that case, transfer these forces to the nodes, write down the equilibrium equations. K11 will be equal to EA over L, whereas K21 will be equal to minus EA divided by L. Now, if you repeat the same for case 2, you will obtain a similar equation. So my stiffness matrix, the element stiffness matrix, for a truss member will have this form: EA over L, 1, minus 1, minus 1, and 1. So this matrix stores all the possible coefficients for a single truss member. The other element type that we see is where we use the modified equation. So I will call it beam member with a hinge. So here the hinge represents that at one end, it could be the start node or end node, we have a free rotation, free to rotate condition. Now, case 1, let's say that hinge is at the end node. Let's draw our member now. That's the start node, and let's put a circle to the end node just to show that the end node is free to rotate. That's I, that's J. Let me put a note here. This is an internal hinge. Okay. Let's show the degrees of freedoms. This is D1, D2, and D3. Remember that we will be using the modified equations for this member, like we previously did, and that's why I don't have to define any degrees of freedom, any rotational degrees of freedom at the end node. Okay, so continue. Case 1. So D1 is equal to 1, whereas D2 and D3 is equal to 0. Again, I'm doing the same thing. Start node, member, end node. Let's show the forces. So I apply K11, that will create a unit translation. I have to have K21 here to keep the rotation equal to 0. K31 to keep the translation equal to 0. So I got only 3 coefficients here. Let's draw the deformed shape. A unit translation that's equal to 1. This end is free to rotate. And let's show the forces. Remember that this time we will be using the modified slope deflection equation. And in that case, for this given shape, the magnitude of that moment is 3EI over L square. At the end node, there is no moment. The moment is equal to 0. Then the shear force should be equal to 3EI over L cubed. And I should have the same shear force but in the opposite direction. And magnitude is again 3EI over L cubed. So for this case 1, for this given case, my coefficients are as follows. Transfer them to the nodes. K11 will be equal to 3EI over L cube. K21 is equal to 3EI over L squared, and K31 will be equal to minus 3EI over L cube. So we finished case 1. Let's work on case 2. So D2 is equal to 1. This time we are giving a unit rotation, while we are keeping D1 and D3 equal to 0. Node member node, I have a hinge here. This time I apply K22 to create a unit rotation, K12 to keep the translation equal to 0, K32 to keep the translation equal to 0 at the end node. And let's draw the deformed shape. This rotation is equal to 1. The deformed shape will look like that. Now the moments, this moment will be equal to 3EI over L. At the far end, I don't have any moment. The shear forces, this is 3EI over L squared, and shear force will be in the opposite direction, 3EI over L squared. Now write down the stiffness coefficients. So K12 is equal to 3EI over L squared. K22 this time will be equal to 3EI over L. And K32 is again equal to minus 3EI over L squared. So if I write, I will not work on case 3. If I write all the coefficients in matrix form, then I have the following matrix. For a beam member with a hinge at the end node, or end node is free to rotate, 3EI over L cubed, 3EI over L squared, minus 3EI over L cubed. The second row, 3EI over L, minus 3EI over L squared, and 3EI over L cubed. So this will be a symmetrical matrix. So when I have an element like that, an element who at the end node is free to rotate, this matrix shows all the coefficients, all the stiffness coefficients. Let's continue. I can have a beam this time with a hinge can be at the start node. Let's work on that too. Hinge is at start node. Let's draw the member this time. The hinge is at the start node. I'm showing it this way. End node. This is joint I. This is joint J. Let's show the degrees of freedoms. That one is D1. No rotation degrees of freedom this time at the start node. D2 and D3. So you'll repeat the same procedure. I will not do it again. I'll just give you the stiffness matrix and write down all the cases. And at the end of the day, we obtain a stiffness matrix as follows. K is equal to 3EI over L cubed minus 3EI over L cubed and 3EI over L squared. The second row, 3EI over L cubed minus 3EI over L squared. And final is 3EI over L. And this will be a symmetrical matrix. And this is the case when we have a hinge at the start node. So we have one more final element. We call them frame members. Remember that truss member can only undergo axial deformation. Beam member can only undergo flexural deformation, and frame members can undergo both axial and flexural deformations. So we actually have all the information that we need. Let's define it. Again, start node, end node, I, J, and let's show the degrees of freedom. D1 is the axial deformation, D2 is the translation, D3 is the rotation, D4, D5, and D6. And if we want to generate the stiffness matrix for it, we will be actually combining the stiffness matrix of a truss member plus the stiffness matrix of a beam member. If you think about the derivation, this is what we will get actually. So you can try if you want, but let me just write it here. It's the combination of the truss member stiffness matrix and beam member stiffness matrix, and we will end up with a stiffness matrix as follows. So K is equal to, sorry for that, is equal to, we will be writing a 6x6 matrix. EA over L is the force required to create a unit shortening. No coupling with the bending deformation, 0, 0, minus EA over L, 0, and 0. So this is the first row of the stiffness matrix, and the first row describes the axial deformation, and the second row is what we have for the beam stiffnesses, 12 EI over L cube, 6 EI over L square, 0 minus 12 EI over L cube and 6 EI over L square. The third row is related to the rotation, 4 EI over L, 0 minus 6 EI over L square, and 2 EI over L. We have EA over L, 0, 0 here, 12 EI over L cubed, minus 6 EI over L square, and 4 EI over L. So as you see, with all these members, we derived all the possible stiffness coefficients that we can see with the elements that we use in the structural analysis. The beam members, truss members, the beam members with the hinges at the start node or end node. These has all the possible stiffness coefficients. So while analyzing a structure, all we have to do is to take the correct coefficient from the element stiffness matrices and put it into the structural stiffness matrix. So we will be solving some example problems with this approach so that you can better understand how this approach works. I will also put a sheet, a document to the METU class website. There you will have all these matrices written, and then we will be using these matrices, these documents, to analyze a structure. Now let's derive the stiffness coefficients for a Timoshenko beam. This time we will include the shear deformations and see what type of coefficients we will get. And if you want to have a frame member that considers the shear deformation, you just combine the bending part with the axial part as we did before. Now remember that we derive the governing differential equation is as follows for the shear deformation. dvs is the shear deformation divided by dx is equal to shear force divided by shear modulus times the effective shear area. And remember that this equation is derived for the following deformation. Remember, this was a square, and we said that this is the shear deformation, and we defined the shear deformation in the counterclockwise direction. Now in the derivation I reverse it. I will use a different deformation. So this is the square, and if I have a clockwise rotation like that, then my equation will become I have to multiply the shear deformation with the minus sign. So for this type of deformation, my equation will become dvs divided by dx is equal to minus shear multiplied by g times as. So this is the governing equation for me for this given deformation. Okay, now what I want to do again, I want to derive these stiffness coefficients for a member. So I'm drawing a member. Okay, so I have this member whose length is L, and let's say that the x is defined from here, and at the at x is equal to L, I have a fixed support, which means that the shear deformation at that point is equal to 0. Okay? Now, let's rewrite the equation star in the following form. The shear deformation of an infinitesimal element is equal to minus V G times AS multiplied by dx for an infinitesimal length. For the total length of the member, if I integrate these two equations, I end up with the following. Vs is equal to minus V G times AS times X plus C1. Okay? Now, if I put these boundary conditions into that equation, I obtain C1 as equal to V times L multiplied by G times AS. So, my final equation, the governing equation for this given member is as follows. Vs is equal to shear force multiplied by G times AS L minus X. Okay, and as you will see, I will use this equation to derive the stiffness coefficients. So now let's determine the stiffness matrix coefficients. So I will again use the right hand side of this paper. And I will use the same approach as we did before, matrix coefficients. So this is our member. That's the start node, that's the end node. That's the first degrees of freedom, D1, D2, D3, and D4. Now let's start from the case 1. D1 is equal to 1, rest is equal to 0. So let's draw the deformed shape. I'll just assume that no shear deformation. Okay, when there's no shear deformation, that's equal to 1. And I know what the forces are. This is 6EI over L squared. This force is 12EI over L cubed. This one is 12EI over L cubed. And rotation is 6EI over L squared. So that's the case that when we have only flexural deformation. Okay. Now, we said that we will be considering the shear deformation. So as you see, I have a shear force on this member. And when we have a shear force, it will cause shear deformation. So let's plot that also. So this part, let's assume that is fixed. No deformation here. So I'll just plot the shear deformation in this figure. So in that case, we will see only angle change. Now, initially, this angle was 90 degrees, but now it becomes smaller. Okay, so I draw this case. Now, how much deformation will I get? Additional deformation. This is the neutral axis. And then afterwards, I see a translation and I see a shear deformation. Let's show it with this symbol. And this shear deformation is called parasitic shear deformation. And in that second figure, I just draw the shear deformation only. So I'm interested in the value of this one because I wanted to have a unit displacement, right? I apply these forces, but at the end of the day, due to the shear deformation, I got more displacement. It's not equal to 1, but it's equal to 1 plus the parasitic shear deformation. So I should add plus here. Now, what is the value of that shear deformation? I will be using this equation now. So at x is equal to 0, my shear force is equal to 12 EI over L cubed. Okay, let's call this one equation plus. So using equation plus, I obtain Vs as equal to WL times G times AS. So put that shear force into that equation, and that will give me the magnitude of this parasitic shear, which is equal to 12 EI divided by GAS times L squared. So at the end of the day, my total translation is equal to 1 plus phi. Okay. All right, let's continue. Now I wanted to have a unit translation, okay? But I end up with a translation that is larger than 1, okay? So since this is an elastic material, in order to get a unit translation, what should I do? Let's put it here. K11, right? K21, K31, and K41. I'll ask the same question again. Now I have 12 EI over L cubed. So in order to create a unit displacement, I apply this, but I get more displacement, which is equal to 1 plus phi. So in order to get a unit displacement, what should I do? I should apply a smaller force. How much smaller? 1 times phi, 1 plus phi times smaller. Okay, so for this case, in order to obtain a unit displacement, I'll draw the same type of figure. This K11 should be equal to 12 EI over L cubed scaled by 1 over 1 plus phi. So I should have the same force here in equilibrium, whose magnitude is 12 EI over L cubed 1 plus phi, okay? And then the moment, this moment is 6 EI over L squared 1 plus phi, and this moment is 6 EI over L squared 1 plus phi, right? So when we don't have any shear deformation, when we have only the bending deformation, these are the first row of the stiffness matrix. But when we consider the shear deformation, the magnitudes of these stiffness values are smaller now. How much smaller? It's 1 over 1 times phi times smaller. Okay, because now we have a more flexible member. So this is the first row. This is the case when we have a unit translation. Now let's take a look at case 2 now. Case 2. Okay, we will have d1, or let's write it this way, d2 is equal to 1, rest is equal to 0. So let's draw this. We don't have any translation now. Let me draw the deformed shape. Now this is equal to 1. That moment is 4EI over L. I got 6EI over L squared. 6EI over L squared. And this moment is 2EI over L. And this is the case when we don't have any shear deformation. Now, at x is equal to 0, the shear force is equal to 6EI over L squared, and Vs is equal to, again, V times L G times AS. And again, if we use the equation star, we obtain Vs as equal to 6EI divided by G times AS times L, which is equal to 0.5 times the parasitic shear deformation times L. Okay, so if I apply the following forces, and if we have the shear deformations, then this is what I see. Shear deformations move the beam by 0.5 phi times L. So in other words, if I draw the deformed shape again, this part is fixed. That's the neutral axis. We tried to bend it, but this is the shear deformation that we got. But this time the magnitude of the shear deformation is 0.5 times phi times L, and the bending deformation is something like this. Okay, so this part shows the shear deformation, this part shows the bending deformation of the neutral axis. But now this is not what we want, because according to our definition, we want to keep the rest of the translations equal to 0. So what should we do? Let's see. Now I will draw that figure one more time. So we have bending deformation only. Let's draw it. And let's show the forces. Again, I got 6EI over L squared, 6EI over L squared, 4EI over L, and this one is 2EI over L. This is the case when we have the banding deformation, but there's a but. We said that because of that, I saw a deformation in the upward direction that's equal to 0.5 phi times L, right? That's what we see. So this is the parasitic shear deformation. Caused by shear force, right? So what should I do? Now the deformed shape that I want to see is I should have only rotation, and I should have the rest that should be equal to 0. So I should apply a force in such a way that it will give me this translation in the reverse direction, but doesn't add any rotation to it. So I want to see this. This is our member. I want to have a deformation like that, and this is the total deformation that I want to see. Okay, and this is the what I'm doing is an equal and opposite translation is applied. Okay, in order to create a deformed shape like this, how much force, what is the forces that I should be applying is written right here. These are the forces to create a unit translation with 0 rotation. But I want the opposite. I want a translation that's equal to this in the opposite direction. But I also want to keep the rotations equal to 0. So how much shear force should I be applying? I'll just show this way. And the magnitude of that shear force should be equal to 12 EI over L cubed 1 plus phi multiplied by minus 0.5 phi L. Okay, I should have the same force, but it should be in the opposite direction. 12 EI over L cubed 1 plus phi minus 0.5 phi L. Okay, the moments, this one, again 6 EI over L squared 1 plus phi multiplied by minus 0.5 phi times L, and I should have the same moment here. Let me write it for completeness. 6 EI over L squared 1 plus phi multiplied by minus 0.5 phi times L, and I should have a plus sign here. And when I add all of it, I will get the deformation that I want. The deformed shape will be as follows, right? Together with the shear deformation, again I will see the same deformed shape. That's equal to 1. No translation because we eliminated the translations due to shear. So when you add up all these forces, here the moment that I will get is this. 4 plus phi divided by 1 plus phi multiplied by EI over L. This one is 2 minus phi divided by 1 plus phi multiplied by EI over L. The shear force is 6EI over L squared multiplied by 1 over 1 plus phi, and the shear force here is equal to the same magnitude, 6EI over L squared 1 over 1 plus phi. And as you see, these coefficients gives the second row of the stiffness matrix. You can actually continue like this, do the case 3 and case 4, and once you do that, you obtain all the coefficients that you need to form a 4x4 stiffness matrix for the bending deformations with shear that involves the shear deformations. And we gave you the matrix in the tables. You can see the stiffness matrix for a Timoshenko beam element.